Not sure why that last video was cut short. We didn't quite get ready to analyze the molecule for our Lewis structure for IBR3, iodine tribromide. We look at this molecule. We've got 1, 2, 3 atoms, and then 2 lone pairs, 2 sets of lone pairs. That's 5 total things around the nucleus, around the central atom, I mean. 5 total things. So we know once again that this is in the trigonal or trigonal bipyramidal family. So we can circle the trigonal or trigonal bipyramidal family. In that family, there are several shapes. There are 4 shapes making up the trigonal bipyramidal family, as we see right here. Which one is it? Well, this is the molecule that has 3 atoms attached to it. We see the 3 bromines, and there are the 2 lone pairs. So we're looking for the molecule that is the 3,2. We're looking for the 3,2 molecule. The 3,2 is what we would call T-shaped. There it is. 3 for the B, 2 for the E. Now we can come down and add our shape formula in. Here's what the T-shaped molecule looks like. Axial atom, axial atom. The equatorial atoms would have been here coming into the back, and then one coming out this way. But instead of having the atoms out there as they would in the trigonal bipyramidal, instead we have a lone pair of electrons going in and a lone pair of electrons coming out right here. That is the shape of this molecule. Let's complete the shape formula. We have AB3E2. Again, the lone pairs are right here on the equatorial plane. There was only one equatorial atom, so we would not have a bond angle between the equatorial atoms. We do have an axial atom up, axial atom down. They would be 180. And then we have an axial up, axial down. They are 90 toward the equatorial atom. So 90 here, 180 between the axial. And now we're ready to go on and take a look at the symmetry of this molecule. We have 2 lone pairs. So we're coming out of the lone pairs. The lone pairs determine the symmetry. When there are no lone pairs, and if it has the same atom surrounding the central atom, it would be symmetrical. So our E is not equal to 0. Our E equals 2, so we go up. Now we take a look down this line. Am I a 2,3 or a 4,2? No, I'm a 3,2, so I continue up. The 3,2 would take us to the asymmetrical shape. The other way to get to the asymmetrical shape would be if we had different atoms surrounding the central atom. We don't have different atoms. They are all bromines. So if we had different atoms, we could come down, and that would also lend us to asymmetrical. We have the same atoms. So now what we need to do is find out if it's asymmetrical and has polar bonds, it's a polar molecule. If it's asymmetrical and has nonpolar bonds, it would be a nonpolar molecule. So we need to check the symmetry of the bonds. We'll do that by looking them up on the electronegativity table. On our electronegativity table, we have bromine and iodine. So we take 2.8 minus 2.5. The difference is 0.3. For this class, when the difference is 0.3, it would be considered a nonpolar bond for this class. That is the way we've designated it. So 0.3 is not greater than or equal to 0.4. So we do not classify the bond as polar. We would classify it as nonpolar. So we can go ahead and circle nonpolar, which means for this class, if it's a nonpolar bond, we call the molecule nonpolar as well. The differences in electronegativities for this class are not strong enough for there to be a dipole of any substantial strength. So those molecules, the IBR3, the iodine tribromide molecules, just wouldn't stick together very well by the dipole. They would have London dispersion forces, however, which are another way they can stick together, and we'll talk about those later in the unit. Our next one that we're going to be taking a look at on our help video here is Xenon Dichloride, XeCl2. Xenon is a noble gas. Typically, it is a noble gas that doesn't want to react, but the halogens do not really worry about that. Xenon can be tricked into sharing with the halogens. So xenon dichloride, there would be one xenon. It is a halogen, Roman 8, 8 valence electrons. There are 2 chlorines in Roman 7, the halogen family. 2 times 7 is 14. We have 22 electrons to work with. Although xenon doesn't want to make any bonds, the formulas give it away when you have an element followed by several additional elements. The first element is usually the central atom. So we'll put xenon in the middle, and then we will attach the chlorines to it. So here's our xenon. We surround it with 8. We'll now attach some chlorines to it. We'll put a chlorine wherever there's a pair. There's a pair, so I can put a chlorine there. Here's a pair, so I can put a chlorine there. And now we need to surround the chlorines with 8. So we've now got 8 around each of the chlorines. Time to check our total electrons. Chlorine has 8 around it. Chlorine has 8 around it. That's 16, 17, 18, 19, 20. We're supposed to have 22 electrons. So we have to add 2 electrons to the molecule. They'll go on the central atom. That's where we add them when we're doing this. So I'm going to add 2 electrons there. I'm going to make this a pair. And I'll make a pair over here. And now we can replace the shared pairs with lines, and we'll be finished with our Lewis structure. So we now have our correct structure, and it is ready to analyze. So we will go ahead and take a look at this to determine what shape it is and determine its polarity and so forth. Let's count the total things surrounding the xenon. We have 2 chlorine atoms, that's 2, and then 1 lone pair, 2 lone pair, 3 lone pairs at 3, that's 5 total things around the central atom, xenon, and right away we can conclude that this is trigonal or trigonal bipyramidal. Anything with 5 around the central atom puts it in the trigonal or trigonal bipyramidal family. The trigonal or trigonal bipyramidal family has 1, 2, 3, 4 different shapes that it could be. This molecule has 2 bonded atoms, 3 lone pairs on it. It's a 2-3. That makes it a linear molecule. So with this being a 2 bond for its B and 3 for its E, we can finish the shape formula. Here's a little schematic of what this molecule kind of looks like. We've got the axial atom still in place. And then along the equatorial, we've got 3 pairs of electrons. One coming out at you, one kind of coming out this way, one coming out to you. They're spread out so that the angles between these electron pairs are about 120. They're along that equatorial plane. So the only atoms we have are the axial, and they are 180 apart. Now we can kind of continue on and take a look at the symmetry of this molecule. So our E is 3, so we come out this way, and we're trying to find out, is it asymmetrical or symmetrical, or one of these 3 choices special? Well, our E is not 0, so we don't go down this way. Our E is 3, so we're going up this way. We first try down this line. Is this a 2-3? Absolutely. We're heading to special symmetry. And the reason they call it special is because the atoms are symmetrical. Atom going up, atom going down. The electron pairs are symmetrical. However, symmetrical itself means same. So the electron pairs are symmetrical. They are. The axial atoms are symmetrical. They are. But there's 2 different things on the central atom. There's both electron pairs and bonded atoms. So there we have different things surrounding it, and that's why it's called special. The atoms are symmetrical. The lone pairs are symmetrical. But we have 2 different kinds of things on the central atom, which makes it a special case. And the atoms are the same. If the atoms were different, if they weren't both, in this case, chlorines on the xenon, the atoms are the same. If one was chlorine and one was fluorine, then it would be asymmetrical. Different atoms puts it as asymmetrical. With this molecule being special, the atoms are opposing each other. So for the most part, we would consider this molecule to be a nonpolar molecule. Because if the atoms are opposing each other by 180, the polar bond If it had polar bonds, the polar bonds would tend to cancel out, one pulling directly opposite each other, leaving the molecule largely nonpolar.